You're muted, Patrick.
That's perfect. All right. Well, good evening, everyone, and welcome back to the Astro Imaging Channel. We've got another great show for you tonight. Rolf Olsen is here tonight, and he's going to talk about his extreme deep field project of the Centaurus A galaxy, which is a really unique object in the southern hemisphere, if you haven't seen it. But before we get to that, I'll just talk a little bit about the upcoming calendar. Let me pull that up here. Share the calendar. All right, so next week, Christian World will be with us, and he's going to talk about the Touch and Stars app which is a neat touch interface for Nina that he's developed. So we're all looking forward to hearing about that. And then Kai Young will be back to talk more about the Sea Star. And he's been on the show a couple of times, and those have been both really popular episodes. Dustin Brimbury will be back then, or will be with us in the beginning of March, and he had previously been scheduled and was ill, and so we had to reschedule, so that'll be coming up. And then you can see we've got a few other things, and we will be taking off the first week of April for NEAF and NEAC, and then we do have open dates in April 13th. So as we always do, if anybody out there, if you've got an idea, something that you were thinking about maybe presenting, we'd love to have you on the show. So drop us a line on the contact page, and we will get you on the show. So stop sharing there. Right, so that then brings us to tonight's presentation by Rolf Olsen. And Rolf had started imaging the Centaurus A galaxy in 2013, and he captured over 100 hours of data that year and produced one of the deepest images, if not the deepest image ever seen up to that point of that particular object. And since then, he's continued working on the project and ultimately ended up with over 300 hours of data. And the final image that he produced is really just mind-blowing. Unsurprisingly, it was selected as the APOD or the Astrobin image of the day in November of 2024, and then an APOD in December. So tonight he's going to tell us about how he worked on that project and produced that image. So Rolf, if you're ready to take over, I will hand it off to you.
All right, thanks guys so much for having me on the show. It's a great honor. I enjoy that. And I'm just gonna...
Real quick, Rolf, before we go, the audio thing where we're hearing just the echo of it and not the mainstream is happening again. Yeah, it sounds like we're hearing, so it's like a microphone up to this.
Has it gone away?
Let me check.
Is the talking head up as well as the main screen, Terry?
No, I have my microphone turned off, and I have it turned off, and I've got two controls, and I got them both off. So it shouldn't be coming from my end. So I'm not sure where it's coming from.
That we've lost all audio altogether.
Why don't we try muting ourselves except for Rolf?
Yeah.
Well, it's not going to fix the fact that he's super quiet.
Chris says it's clear on YouTube.
That's
sounding okay on YouTube now? Is that what we're hearing?
It still sounds quiet to me.
Are you listening to it, Molly?
Yeah, yeah.
Okay. How's
People
it
are saying
sounding now?
it's better. I just refreshed my page, but
Is it that the audio is low, or is it that echo issue?
well, people are saying it's fine now. It still sounds weird to me, but if everybody else can hear it, then we're probably good to go.
The audience thinks it's okay? All right. That's tough, yeah, because it's hard for us to hear you.
Yeah.
Yeah, I know.
Sounds good in the meeting.
Usually the audio, like the video at the beginning played full volume, so I don't know.
All right, well,
But
hopefully we're
people
good
are
to go.
saying it's fine, so.
Okay, is the
Benefit being live, you know.
okay? From what I
So
can,
will you be able to grab the stream, Molly, and pick it up?
I should.
What-
I think we succeeded this last time.
okay, what I can see here is the audio is going out, but is there still an echo?
Well, it wasn't an echo. It was more like the audio, like we were listening to it through a speaker or something. But people are saying that it's fully gone now.
Yeah,
Good. They can't hear us at all.
Now, right now, there's no audio at all.
Okay, I'm gonna try and steal the stream from you.
Okay.
No worries.
All right, well, hopefully Molly will be able to stream here and without terminating it.
Can you guys?
You got
it? There
Take
you
a couple
are.
By
seconds
the
for
way,
us
the
to
audio
start.
just returned, and it seems to be okay now.
You can hear it now. It sounds all right. Jaime, are you listening to
kind of,
YouTube?
Yep.
All
Bob
right,
Bryant
great.
says the audio's back on main too.
Okay, perfect. All right, well, with
All
that,
right.
sorry, folks, and sorry, Rolf, about that delay, but hopefully we've got it squared away, so it's all yours.
All right, thanks, guys. So thanks very much for having me on the channel. I've been looking forward to this presentation, and I hope that I can tell you some interesting things about a little project that I've been working on for a little while, actually a bit over 10 years now. Not all the time working on it every day, obviously, but sort of on and off with a few different imaging periods. So I'm going to talk about my extreme deep field image of Centaurus A, which is a very prominent galaxy, one of the brightest in the sky, actually. And it's very clearly visible to us down here in New Zealand, passes straight overhead. I grew up in Denmark, where you can't see Centaurus A at all. So, but still, I saw images of this galaxy in books and stuff as I grew up. And it always seemed like a very fascinating and iconic galaxy with that dark dust lane slapped across. So it was very exciting to actually be able to see that when I moved to New Zealand and start taking pictures of it. So it's one of the most fascinating objects I think we have in the southern sky. So let me just give you a bit of background about myself to start off with. I grew up in Denmark, and I've been interested in astronomy as far as I can remember since my early childhood. In 2003, I moved to New Zealand just to enjoy the scenery, the climate. Climate is definitely better than in Denmark, and then the beautiful southern night skies. and I today live in the Waitaka Ranges, which is like a forested area west of Auckland, which is the largest city in New Zealand on the North Island. So my specialty when it comes to astrophotography is high resolution deep sky photography. So that means a fairly narrow field of view, and the resolution in my images are like less than 1 arcsec per pixel. I think it's around 0.77 arcsec per pixel at the moment. My favorite.
Give us just a minute. Molly, could you check it? It seems that YouTube stopped streaming.
Yeah, just hit the refresh button and then hit play. It'll come back. I've got it up.
Yeah, okay. I think it's going.
Yep.
All right. So favorite targets for me are unusual or rarely imaged objects. There aren't that many of those though, but I also like to do familiar objects in a new way. So this Centaurus A image is an example of that. So I like ultra deep images. I like taking pictures of stuff like light echoes, gravitational lenses. Many years ago, I took a picture of the circumstellar disk around Beta Pictoris, which got in the news all over the world. So that was quite a fun experience. And I've observed and photographed the night sky since I was a teenager, basically. So in 1990, I got my first telescope. It was a standard 60mm refractor. A couple of years later, I swapped it out for a 100mm size refractor on an equatorial mount. And then in 1995, I purchased a 10-inch f5 Newtonian. I did some brief experiments with film astrophotography, but I didn't really have any sort of equipment of my own. I was borrowing stuff and just playing around, and I didn't really get far when it came to film photography. In 2003, I started playing around with a long exposure modified webcam, the Philips 2U cam. That was all the rage back then. So I took pictures of the moon and the planets and some of the brighter deep sky objects with that one. And it was great learning experience for me to start actually taking real digital pictures of the night sky. Then in 2004, after I'd moved to New Zealand, I built my first observatory, which is the one you can see on the bottom left. And that was just a simple garden shed that I modified to have a roll-off roof. Then a few years later, we moved house. I built another observatory, same construction really, with a roll-off roof, but the building materials and the sturdiness was a bit improved. Then in 2011, I built a 12.5-inch f4 thrust tube Newtonian reflector, and I got a CCD camera, and that's the instrument I'm still using to this date. Then in 2013, I set all that up in my third observatory, which is then an automated dome. And I have a picture of that here. So this is a scope dome, if anyone is familiar with that. It's like a fiberglass kit set that you can purchase, and you can fully automate it. So as I said, this is the observatory site is in Auckland, New Zealand. My skies are not fantastically dark, but it's what we would call dark suburban skies. I can see the Milky Way, and I can even see it like when the moon is up, I think. But yeah, it's fairly faint. And I think over the last 20 years that I've lived here, I think the light pollution has certainly made inroads into the darkness of my skies. But yeah, it's still reasonably good for a city of more than 1 million people. The elevation is 240 meters, and as I said, it's all set up in an automated dome. You can see here my my setup. You got the telescope on the mount. There's a thrust tube telescope, but there's a shroud around it just to prevent scattering of light. There's the main camera there up on the right. There's a guide camera attached to that. So the main camera is a QSI CCD camera. It's fairly old now, but it's still going strong. The mount is the Losmandy G11, and you got the primary mirror there, which is an RF Royce mirror, so fairly high quality. It's a conical mirror. I got that because it has lower weight and it's very easy to mount. It just mounts with a bolt in the center, and you just need to make sure your mirror cell can basically pivot. So it was quite easy to construct a homemade telescope in this manner. And then you got the dome controller down there, which is like a big box that controls the whole dome and automates everything and makes sure that the dome is tracking where the telescope is pointing. And all this is then controlled by a little computer on the pier itself, and then I log in remotely to this computer. Just a few pictures of the construction of the observatory, just to sort of get a feel for the site. So this is Auckland is reasonably flat, but we do have some hills. This is quite high up in the hills, so I do have a quite good view in most directions. And you can see the construction there, the foundations, a bit of a wooden deck, and then the ring, the bottom for the dome there, and then the dome coming together in the end. Now, when it comes to the remote controlled operation, as I said, it's controlled by a mini PC on the pier. I use ACP observatory control. So that controls the telescope, the camera, the filter wheel, the autoguider, the focuser, and the dome all together. So I can let this run all night, fully automated. Of course, every now and then the odd hiccup will happen. The scope is not pointed the way it should, or the way that it thinks it's pointing. That kind of stuff happens, but it's not too frequent, really. So having this automated setup really helps when it comes to gathering a lot of data and creating 100+ hour images. I use MaximDL for the image acquisition and the guiding. Again, this is controlled by ACP. It uses Focus Max and the ASCOM mount driver, and there's a driver for the scope dome itself. And as I said, the mini PC that then controls all this is accessed remotely. So I can basically be anywhere in the world and control the telescope. But I usually just sit right inside my house with the observatory like 10 meters outside in the backyard. All right, so my workflow is typically that I'll capture the image in MaximDL and Focus Max, so that's the data gathering. After that, I do the image calibration in a piece of software called PixInsight. So that involves the dark bias flat calibration. Then there's the image processing itself. I use PixInsight for most of that, but then I use Photoshop for the final combinations and touch-ups and layerings and so on. And then the image analysis, also PixInsight, Photoshop. So by that I mean, you know, if you want to look for particular focus on particular areas, if you want to see the difference between an image taken at a different time versus now, see if there have been changes or variable stars, that kind of stuff. Astrometry as well, searching for features and just do certain enhancements and isolate them to certain parts of the image. You can do that in either PixInsight or Photoshop. Sometimes I create videos as well. So educational videos. It's not like I have a ton of those, but I have a couple of those with just some projects I've done. Or I make animations. So this could be in-body simulations of galaxies. I have like a star field fly-through that I made for some images. Light echoes as well, just to animate how the echo propagates across space through time. So I have a couple of videos on that. All right, let's talk about Centaurus A. So as I mentioned, this is a galaxy in the southern sky in the constellation of Centaurus. It's about 11 million light years away. and it was discovered by the Scottish astronomer James Dunlop in 1826. I believe he used a 9-inch telescope to do that. It is the closest active galaxy to us and one of the most studied. It's a fairly iconic galaxy. I think even people who are not really that into astronomy have probably seen an image of this galaxy somewhere. It has an active galactic nucleus, so an AGN in the center, so a supermassive black hole. And this black hole is emitting relativistic jets at its poles coming out. And this galaxy is one of the strongest radio sources in the sky, and it has these massive, famous lobes of radio emission coming out on both sides of it. Interestingly, there is an optical counterpart to these jets, which you can see in some images and in my image as well. And in this overview here, you can just see the jets. There's an image of X-ray in the middle from Chandra. There's an image of the radio emission lobes, so you can see they basically follow the same structure there. There's some much bigger lobes that extend much further out. There's an image to the left showing that. And then the galaxy itself is also like an irregular galaxy. So it has basically merged with other galaxies many times in the past, probably. And as a result, you got all these shells that are evolving around the galaxy from all these different merger events. So the image on the top right is a very enhanced image from a study that shows all these different shells. So it looks very sort of exaggerated, high contrast image, but this is to bring out all the different shells. And this is one of the things I wanted to bring out in my project on Centaurus A. I wanted to create an image that could show all these different features, the jets, the shells, the dust lane, all these little details in one image, because at the time in 2013 when I started on this, I don't think there was an image like that. So I wanted to show that. And at the bottom right, you got a nice Hubble image of the zoom in on the dust lane. It's just amazing to see the amount of stars and detail that we can see there. Okay, so I just want to show here that astrophotography is a journey. I'm very happy with the latest image that I managed to get on Centaurus A, but I just want to show everyone that this is not where you start out. You can see my image from 2004. This was my first image of Centaurus A, taken with a modified webcam. It's 79 frames of 15 seconds each, and it's full of noise. The collimation is horrible, and you can barely see what's going on, but it shows the dust lane and that sort of glow in the center, and it looks all mysterious, and I was very happy when I managed to take this image. Jump forward quite a few years. This is my first CCD image of this galaxy, so obviously much better quality, more resolution, better colors. The processing is better as well. And then another year later, I took my first 100-hour image of the galaxy. So you can see it's just a quantum leap forward, but we all have to start somewhere. So this is definitely a journey, and it evolves, and technology keeps getting better. The cameras keep getting better. The telescope keeps getting better. So who knows where this will go. Okay, so one thing that I've always been mindful of, or at least in the beginning when I started taking CCD images, was to not just blindly try to take the longest single exposure, but you got to have a lot of sub exposures, and you got to stack them together, so you can take advantage of rejection algorithms to get rid of noise and hot pixels that move around, and all kinds of things, like a plane that suddenly passes in front of your image, or some of Elon Musk's many Starlink satellites that keep coming across. It's just amazing how much stuff there's actually coming into your images from time to time. So you need a lot of different sub exposures and stack them together to do that. And the question is then, what is the optimal sub exposure time? Is it 1 minute? Is it half an hour? Who knows? But there are actually ways to calculate that. And it depends on a lot of factors. So it depends on your own imaging system, your telescope, your filters. It depends on the brightness of your local sky. It depends on the camera you're using and so on. And as I said, a long sub exposure is not necessarily the best. Obviously, if you have a very dark sky and you have nothing that's going to interfere with your imaging, then you would probably want to tend to go for longer sub exposures. But the reality is that if you go really long, like 1 hour or half an hour per sub exposure, if you lose some of those, you're actually losing a lot of imaging time. And there can always be a bird landing on your telescope or a gust of wind or something that cause a particular sub exposure to not be useful. And then you have actually lost a lot of time. So there are calculators to figure out what's the optimal sub exposure. And then you can decide, is that the sub exposure you want to use? Do you want to maybe modify that a bit up and down? In my case, I tend to use 5 minutes as my sub exposures. I find that's a good trade-off, and it's pretty close to what's the actual optimal exposure for my my particular setup and my local conditions. And it means that if some of these exposures are lost because a gust of wind happened or whatever, it's not at the end of the world to lose 5 minutes here and there. All right, so for a project like this, obviously you want to get as much data as possible. So I had to plan my imaging sessions. This, of course, as I said, means consider the optimal exposure times, have an idea of how many exposures you need to get. But if you are having like a 100+ hour project, this will go on probably for a season or two. So you need to adjust for the changes throughout that season. Your target is going to change altitude. It's going to rise at different times. When the meridian flips happen is going to be different every day. The moon phase is going to change throughout your project. Obviously, the weather conditions are going to change. The seeing will be variable. So I recommend you take luminance imaging in the best seeing. So when you notice the seeing is really good, just switch to luminance, because luminance is what gives you the detail and the crispness in your image. If you're doing LRGB imaging, that is, so with filters, not one-shot color. And then in the interest of getting as much data as possible, you can actually keep going when the moon is up. Obviously, the easy solution is to switch to narrowband. In the case of Centaurus A, these hydrogen alpha jets that are awesome. So I took a lot of narrowband during the moon when the moon was up. But you can actually take other channels as well. You can take near infrared. You can take red or even green. Perhaps not at full moon, but at least at half moon. I've not really had issues with red or green channel, interestingly. Obviously, in the worst case, you just got to switch to something else, bright targets, open clusters, globular clusters, something like that, where the moon doesn't really interfere much, where you're not imaging something really faint. On this slide, you can sort of see my my attempt at organizing and planning this a bit. So up here, there's like a spreadsheet where I keep track of all the different dates that I've taken images and what frames I took and what's the exposure time, how many frames. And then my spreadsheet can calculate the total exposure time in each filter and the overall grand total. And this adds up to a lot of data. All these frames then have to be calibrated and so on. And I'm the type of person who never really throws anything away. So I keep all this stuff because just in case. And that was handy in this case, because 10 years later, I decided to carry on with this project and take another 150 hours or so. And you can see here my Centaurus A folder is around 250 gigabytes. And I think that's just the latest folder, actually. I think I have another folder with the old data as well. In the bottom left, you can see the image gathering. So this is maximum DL, just cracking away night after night. So you can see Centaurus A, the core there, and the exposure is happening. On the bottom left, this is from another project. I didn't have an illustration of the Centaurus A gathering in this format, but I just wanted to show. So you got the dates at the bottom, and you can see the white, red, green, blue data gathering, and you can see that I've taken different channels at different times. So for this project, I took quite a lot of color data early on, apparently. So I think the seeing was probably not good at that time. So I switched to color channels, and then later on the luminance shoots up and the color amount stays the same. So I think I had some weeks there with good seeing, and then you can also see how it sort of tapers out, and I get less and less progress over time, because in the end there's just less and less time to image this object because it just keeps setting earlier and earlier. So that's kind of how your curve will go. It'll go up rapidly in the beginning, or in the middle it'll go up rapidly and then fade out. Okay, so speaking about having a lot of data, this is an example of what you get out of having a lot of data, and of course you can argue that they're diminishing returns. I would say as long as you're having fun, then keep cracking. I was having fun with my Centaurus A image. I thought that 100 hours was a lot, and then I ended up taking more than 300. So that's just how it goes. But you can see here, this is again from another project, but the point is the same. So up here on the left, you got a little crop of a single frame where there's a background galaxy. So you can see all the noise. This is a single 5-minute frame, lots of noise, and you can just, there's a hint of the galaxy there. Then we go to 1 hour integration, 3 hours, 6 hours. So every panel is approximately double the exposure time. And you can see how the noise disappears. I'm not sure whether that's clear on the YouTube with the compression, maybe not, but it does get a lot smoother towards the bottom right. And then on the right side, you can see the corresponding crop of the final image with all the colors and the actual image processing. So it looks different. But this just shows that the more data you have, the easier it's going to be to work with, and the better the end result is basically going to be. And personally, I prefer to take a few images a year that are of a high standard and show something interesting, rather than try to take 20, 30, 40, 50 images of all different kinds of things. When I started out, I certainly pointed my telescope at everything, like many different targets a night, and tried to capture whatever I could. And it was just exciting to play around with. But I've tried to become more focused on do like a few good projects these days. Okay, and this is just a brief view of the of that image from this project. So the galaxy we were looking at is the blue one here at the bottom middle, just so you could see the final result. So this is the Antlia cluster extreme deep field, 152 hours. I did this one after I did my first Centaurus A image, and this one was actually selected as APOD back in October 2016. Okay, so over to the Centaurus A image. So this is 2013. This was the 120-hour image. At the time, I believe it was the first amateur image with over 100 hours of exposure. The limiting magnitude from what I could measure was around 25, which was quite deep. it was also one of the few images that showed these large H-alpha filaments from the jets. So at the bottom left here, you can see there's an inner jet and an outer jet coming out. And there are both some red and blue parts to that jet. And that was very exciting for me at the time. And there was certainly more detail in this image than in images from like the VLT and so on. Obviously not when it comes to resolution, but when it comes to depth and the actual detail in the jet. So I was very happy with that, and it was very encouraging for me to see that as an amateur, you can actually just collect a whole lot of hours and you can get something that's quite unique, because the large observatories are not going to spend 100+ hours on an image like this. They're going to do very targeted observing campaigns. So one other thing that interested me in this image was that there is a tiny red smudge up here, and I have another slide on that. But this actually turned out to be the first optical detection of the southern jet of Centaurus A. So in my image, south is up, north is down. I know that that's probably a matter of taste, but I prefer my Centaurus A image this way. So the northern jet is showing going down, and the southern jet is actually showing up here. And we can't see the southern jet apart from this little red blob because it's pointing away from us. I have another slide that talks to that. Another highlight here is all these shells, and if you recall the image I showed earlier from the study with the enhanced shells, you can see a lot of these shell details all the way from the core. There's a very bright circular one, an arc here, and then lots of shells all the way in the halo. So you can really see how this galaxy has been merging with other galaxies and producing all these shells. Another thing that you can't immediately see in the image, but they are there, there are actually 709 of the known globular clusters of Centaurus A. And that's quite fascinating, because our own Milky Way only has around 170 or something. Centaurus A has a couple of thousand, and in this narrow field of view, you can actually see more than 700 of them. So this image was taken from February to May 2013, and it was, as I said, 120 hours all up. Then in 2018, I did an update. I didn't gather a lot of more data, but my processing skills had improved. I was able to make a sharper version, and I added 10 hours of narrowband imaging because I wanted to really show the jet. So when you see the jet in this image, you can see there's a lot more detail. It's really bright red, and also the hydrogen alpha nebulae in the dust band there. And all the blue stars are much more defined and crisp. And yeah, I reprocessed the image, and I think I brought out the detail in a bit more natural way and with more detail. Actually, it's always a trade-off in a project like this, like getting the most detail without making it look artificial. It's a challenge, but I was happy with how this image turned out. All right, I just wanted to talk about briefly the southern jet here. So on the right, this is a collaboration image that NASA did with my optical data, and then X-ray data from Chandra and infrared from Spitzer. So you can see there's a tiny sort of orange blob here, and this insert is my optical image where you see the same reddish looking blob. So at the time, I noticed that there was this blob in my image. I could of course not prove what it was, but I speculated that it might be part of the southern jet that nobody had seen before. And I noted that in my image description. And then in 2018, a study came out that actually confirmed that this was indeed the optical counterpart of the southern jet. And I did receive an honorable mention in a footnote in this study, that they had noticed that this emission feature actually appears in my image from 2013. So that was special to sort of be the first to see this optically. Okay, so with all that done, I turned my attention to other targets, but of course I love Centaurus A, and I did get the suggestion at the time that I should make a mosaic and expand the field of view, because Centaurus A has a very large halo that goes beyond what you can see in my fairly narrow image. And I was sort of thinking, oh yeah, and ultra deep mosaic, that's crazy. It's gonna take forever. It's too much hassle. It's not worth the effort. It doesn't really bring anything new. But of course, it would be fun to do. Why not? So that's what I ended up doing last year. I usually maintain a to-do list of targets, and then I thought, well, I'll take a bit more hydrogen alpha on the jet, and then I ended up taking some more LRGB imaging and expanding the field of view. So again, I started collecting more data. You can see my spreadsheet here. This is actually only for the narrowband images. So lots of nights of imaging. So all up, I ended up with 321 hours. That's combined with the 120 I had earlier. And that's with 126 hours of hydrogen alpha and oxygen 3. And this time I wanted to obviously expand and have the mosaic and have the entire view of the galaxy and see if the jet extended further, because as you have probably noticed, it's cut off in my earlier images because of my narrow field of view. And there are other images that show the jet extending further. So I was aware that this carries on outside my field of view. So you have the mosaic there. These are just like raw images from the camera, just trying to piece them together and see what would this actually look like. So four images together would give me a big enough field of view for what I wanted to show. And you can see at the bottom here, you can see the hydrogen alpha on the left, a single frame. So my hydrogen alpha exposures are 15 minutes instead of 5, because there's just a lot less light coming through the very narrow filter. You can, I don't know whether it's clear on the YouTube, but there's a very faint trace of the inner filament. There's a faint smudge that sort of represents the outer filament. On the right side, you can see 73 hours stacked with all the stars removed, and you can see it's a different story. There's a lot going on, and there are a lot of features in this jet that I had not seen anywhere else in any other images. Close to the galaxy, it almost looks like a sort of a thundercloud sprite thing coming out in all directions, and yeah, just a lot of stuff going on, and it carries on to the edge of my field of view, really. So that was very motivating to see that. I could see this emerge as I kept gathering data. I would do some test stacks and just see what I was looking at, whether I needed more data. So this sort of slowly peaked out at me, and I could see that there's a lot going on. And also in oxygen 3, there's quite a lot going on. Not further out, but in the brightest part, there's quite a lot of oxygen emission as well. So this is the resulting image. So the 320 hours in total, and this is the traditional version with all the stars, the entire star field. And because this is a mosaic, it looks a lot more crisp because you're actually looking at 4 images pieced together. So you can see the jets there that we talked about before. You can see all the shells, and then obviously the colorful star field and the distant background galaxies, like sort of puffy looking galaxies down here, and like a spiral up here. And there's some interesting colliding galaxies in the background here as well. Then I also made a starless version. And this was kind of my main goal with this image, to really show all the features of Centaurus A in one image. So starless normally means that we remove all the point sources. So usually this is done with an image processing tool, and these days it's typically AI trained to figure out what is a point source and what is an extended source, and then separate it all out. And it's really useful when you do image processing to be able to isolate the galaxy or the nebula, whatever you're working on, from the star field and have them as separate layers. However, it does not know what is a distant background galaxy that's just a point source, or what is a quasar. It will just erase all point sources from your image. And that's not what I wanted with this project. I wanted to present it as it would look if we were outside our own Milky Way. And I'll get into how I did this. But as you can see in this image, you can see the field of view is much bigger. You can see there's more shell details much further out. It's almost like a line going through the galaxy in the direction of the jets. Yeah, it's just interesting to ponder that every single speck of light in this image is a distant galaxy or a quasar or a globular cluster of Centaurus A. There are 1,108 globular clusters in this image that are cataloged. And here is an overview of the different things you can see in the image.
So Rolf, before you go on there, sorry to interrupt, but we did have a question, and you were just kind of on this subject. But Mark had a question about those shells, and are they arms of the galaxy, or sort of, just trying to understand kind of better what they are.
Yeah. All right. So the shells are caused by when two galaxies merge, the cores will kind of orbit each other and sling out stars that then go into very eccentric orbits. And from it's almost like an onion ring, an onion shape with all these different shells that then expand over time. From our vantage point, it's like we're looking through that and we just see like the onion sliced. We see the thick edges of the shell from our perspective, right? So from another galaxy, this will look different, but it will probably still look like shell stuff, just different shells.
So it's
I
just
actually
like
have,
ripples, I guess. Would that be a
sorry,
way to
what
think
was
of
that?
it? Is it like ripples, sort of each
Yes,
one?
you can say it's like ripples. It's like ripples, right?
Okay.
So if you throw a stone in a pond, the ripples will expand, and it's a little bit the same way when the dense cores of the galaxies orbit each other. So I do have a video here. I have a link here, which shows it's like an in-body simulation. It shows how these shells actually form. I'm happy I have the video here on my computer. I can switch over and play it, but people can also see it just on YouTube. I don't know whether it would come through well on the stream itself, but there's a YouTube link here. So yeah, that's how they form, and obviously that takes millions and billions of years, and we're just seeing a snapshot in time of how these shells present at the moment.
Sure. Well, I'm sure folks can check out that video, and
yeah, I'm gonna go.
Maybe with the audio issues we had earlier, we'd probably stay away from playing another video.
Yeah.
I'm gonna go find it and put the link in the chat.
Yeah, great. No worries.
We also had a question about how you remove those stars and the globulars and whatnot, but it sounds like you've got that more.
I have some slides on that. Yes, so I'll explain that. No worries.
Great.
Okay.
Thank you.
Okay. So things to see in this image, apart from the shells, obviously there's the dust lane in the center. So this is believed to be the remnant of a fairly recent merger with another galaxy. So another galaxy came too close to Centaurus A, got ripped apart. probably an ordinary spiral galaxy that typically has a lot of gas and dust, and we're just seeing this gas and dust happen to lie in front of the galaxy core from our point of view at the moment, sort of stretched out into an S shape there. There is a blue arc as well. I'm not sure how clear it is to see on the stream, but there's a blue arc down here below, and this is another remnant of a dwarf galaxy that was ripped apart, and people have calculated that this happened around 300 million years ago, and we can just see the remaining stream of that. We actually do have similar streams in our own Milky Way. They are not bright or anything, but they can be detected in like data that we do have similar remnants of galaxies coming too close and being distorted by the bigger galaxy. We can also see obviously the dust band here, but we can see there's some dark patches that actually cover a lot of the halo. They extend all the way up here towards the upper left and a bit down sort of towards 4 o'clock here. And as I said, you can see the halo extends all the way up. There's like a huge shell on the outer edge of it, and there's like a line and a few shells going down the opposite way. And then the jets themselves, right? There's the inner northern jet, so the inner filament, and this sort of bright line is very easy to see in most images, but all these faint extensions I don't think have really been imaged before. A few of these blobs have, but not all. This sort of it almost looks like a lightning structure. It's really quite interesting. I have an image that shows it in a little bit more detail. And then there's the outer filament. It's obviously all the same thing, originating from the black hole jet, and then illuminating and exciting the gas that's further out and causing it to glow. But it's kind of divided into 2 parts, and you can see the outer part carries on quite a while and then sort of fades out into a few faint blobs here. But there are lots of little details, and I think there are quite a few parts of this that have not been imaged before anywhere. Just a close up on the inner part there. So again, this is the starless image. Even though it's full of dots, every single one of these dots is either a globular of Centaurus A, or a background galaxy, or a quasar somewhere far out. You can see the dust band, you can see that blue arc, and you can see the inner part of that jet filament. So the blue light here is from oxygen, and the red is from hydrogen. And you can see the dust sort of being silhouetted against the background glow of the galaxy here, all these little patches of dust. Okay, so just talking about the jets. So as I mentioned in the beginning, Centaurus A is one of the closest active, it is the closest active galaxy to us, and is one of the most studied. It has a giant supermassive black hole in the center that's causing these jets to come out. The thing that happens is that the radiation, but when the jet moves towards us, it causes the radiation to emit towards us, and we can therefore see the northern part of the jet here, which is on the right side. There's a similar, we must assume there's a similar jet coming out in the opposite direction, but we cannot see the optical emission from that. We can only see it in radio. However, we can see that red part, which is more prominent in my new image here than it was in the old one. So altogether, this is kind of the optical jet system, the very large northern one, and a little red dot on the opposite side of the core. The inner filament is around 30,000 light years from the core. So these are gigantic structures. And the bright part of the outer filament starts around 65,000 light years out, and then it carries on. So if this is 65, what are we talking about? 100 light years, 100,000 light years plus 100, 150 maybe. So these are very, very large structures. The whole galaxy is quite a bit bigger than our own Milky Way. All right, so removing the foreground stars, I'm going to show you how I did that. I'm going to show you using another project I did. I won't go into all the details about that project because this one is about Centaurus A, but I'm just going to briefly tell you what it was about. So this was an attempt to take an image of what's called the cosmic web. So when we see all these fantastic computer simulations of the early universe, we see all these sort of spider web like structures that the galaxies are arranged in. It's like a web, almost like a sponge, soapy structure at massive scale. And when you look at galaxies that are really far away, you can actually see that they often form, they cluster around these web-like structures. So they form long tails or long strings. And I wondered whether it was possible to maybe see that if I could get rid of all the foreground stars and then have only the true extragalactic background, and maybe I could see the structure. So in the top left, you can see the resulting image. And even though my field of view is quite narrow, as I explained, I think you can sort of see that there's a tendency for these galaxies to not be distributed randomly. It's not just random noise. They are clearly distributed along some kind of structure, similar to what this supercomputer over here is showing. So again, every point of light in that image is a distant galaxy or a quasar. There's nothing else. And in that frame, there's more than 20,000 of those. And the origin of the cosmic web are these tiny fluctuation in the dark matter distribution that happened immediately after the Big Bang, right? So the Planck satellite is famous for having actually taken a radio image of these fluctuations, and later in the evolution of the universe, these differences evolved into these very large structures that kind of govern the whole universe today, gravitationally speaking. So just briefly, where is this image from? So this is an empty-looking field. It's about the size of the full moon. The full moon just barely fits on my imaging chip. I chose this area because there's almost no obscuring dust or hydrogen emission. Actually, whenever you look at the sky with a telescope, you're more likely to point in a direction where there's something in front of us, something that prevents you from seeing really far away. Even though we can always see background galaxies in our images, but if you want to see something really far away or have a really deep limiting magnitude, you need to choose a spot where there's the least intervening dust or hydrogen glow in front, because it really just acts as light pollution. So the obvious choice for me was to image the field where the Hubble Ultra Deep Field was taken, which is in the Fornax, and that also happens to be a southern constellation. And you can see here, this is the image, and I've just quickly overlaid the various Hubble study fields. So Hubble has made quite a few images of this area for various purposes, and some of them are sort of wide field when it comes to Hubble, and some are a narrow field, and we have the famous Hubble Ultra Deep Field and the Hubble Extreme Deep Field, which are just tiny squares in the middle of my field of view. This is a 60-hour exposure, so it is not super long compared to other images I've taken, but it's still long enough to show a lot of interesting detail. But I wanted to talk about how I removed the stars. So the process for that, and I really hope that someday we can probably automate this with AI or something, but at the moment, what I've had to do for these projects is to compare with catalogs. So we have all the lovely Gaia data release 3 data, which you can find online. So you can download all that, import that into Excel or your tool of choice, and then you can start filtering it, because the Gaia data is all about stars. But again, the Gaia data has all the different point sources that are available within your chosen field of view. But it has fields to show the probability of it being a quasar, or the probability of it being a galaxy or a globular cluster. So you can start sorting on that and filter out. So you have a catalog of what are the true foreground stars in your chosen field of view. And once you have that, you can create a custom catalog that you can use in a piece of software like PixInsight. And then you can start comparing between what you're seeing and what you now know are actual true foreground stars. So in the bottom left here, you can see this is the just default stretch of an image. And then the little crosses are all the actual stars in the image identified by the Gaia data. So you can see there are quite a few foreground stars, but also there's a lot of background information. Most of these really faint dots are actually background galaxies, because at that depth, it's just outside our galaxy already. So the challenge becomes how do you remove all the foreground stars and then retain the point sources that are actually the background galaxies. So what I do is that I take my original image and then I remove all the point sources using some AI tool. And these days, Star Exterminator is sort of my tool of choice for that, but there are others as well. But as I said, they will remove all the point sources, because the tool cannot know what the point source actually represents. So you can see up there, you have the original image, and you can then split it into the starless background, and then the sort of AI generated star mask. So just the stars alone, and then the background together forms the image. Then you can use your image processing tool of choice. I use Photoshop for this particular purpose, to compare that AI star mask to the image that are annotated with all the real stars that I know are foreground stars and are not background galaxies. And then you'll see there's quite a big difference. You can see the AI mask here is full of dots. And when I have removed all the point sources in that mask that are actually background galaxies, you can see I'm left with this, what I call the Gaia star mask. So these are stars that are in the Gaia catalog and nothing else, no background sources. When you compare the two, you can see it has a lot fewer sources. So a lot of what we see in the image are actually background objects. And you can see the result there in color. So this is the final star mask for this Hubble deep field area. So it's just completely black except for the stars, but it contains every single star that truly are in the image, and then nothing else. So we know that anything else in the image is a genuine background source. And then obviously, now you can actually remove the foreground stars. So you can take your original image up here, you can subtract the star mask, and then you're left with the background only. And so this now represents the true background, as if you had traveled outside the Milky Way and you only look at the distant sources. So every single point of light in this image is a background galaxy or a quasar. There's nothing else remaining. And I pull up this image sometimes on my screen and look at it again, and it's just fantastic, I think, to be able to see something like that and just imagine that every point here is an entire galaxy with billions of stars and who knows how many planets, and whether there might be life out there. But as I said, you can see these strings of galaxies. You can see that they are not randomly distributed. They follow a large structure. So I think this is probably the only image I'm aware of that sort of shows this cosmic web structure, this optical structure. There are lots of images made from like 3D visualizations of the of galaxy surveys and all that, where you can see that they actually form structures, but I haven't seen an actual optical image that actually shows this. So that was quite interesting for me to do. Having these layers, obviously the next step is to do some kind of 3D visualization. So I have another video that people can have a look at, and the link is there. So this is like a fly through where you like fly outside our galaxy and you see the true background, and there's an explanation of the cosmic web and what it is and what it means. So go and have a look at that one if you are interested in that. So that's the story of how the stars can be removed. It's a fairly long process. Even though it was a long explanation, I probably make it sound easier than it is. There's a lot of fiddling. It's not straightforward because you have to do a lot of hand editing in a tool like Photoshop to actually get rid of this. It's not just a simple subtraction between the AI star mask and your catalog. It doesn't really work like that. Then there are a few things remaining. So I hope that that we can come up with a sort of an automated way of doing that. That would be nice. But let's see. Now back to Centaurus A. So applying this process, you can see what's possible. So in the top left, this is like a small crop of the area that has the inner, the outer jet filament and a bit of the shells there you can see. So everything is combined in this image on the top left. So that's the stars and the background galaxies and the jet and the whole lot. I've then got the foreground stars as a separate mask, so I can subtract that, and you can see on the right, then we are left with what I call the true starless version. So it still has lots of point sources, but we know for sure now that these are not stars. They are extragalactic sources. They are globular clusters or distant galaxies or quasars. And you can see it gives a whole different perspective on things, and it shows how many of them that there really are. It's hard to see in the original version because the stars become quite overpowering. So it's very useful to be able to remove that. And a few more examples. So you got the all the extragalactic sources here. I am able to create that as a separate layer. So if I subtract that as well, and I've made another catalog using the same method that contains all the globular clusters, I can suddenly isolate what they are. So you can get a version with these dots here where you then know that they are actually globular clusters in Centaurus A. And again, you can then remove everything and just be left with the shell structure alone and nothing else, which is an interesting view as well. And at the bottom, you sort of got the more traditional hydrogen alpha, oxygen, and the combined, just to see how that hangs together. So those are also taken in separate filters, and they have to be combined to create this color view. All right, so just to show, this is an example. This might be a little bit small on the screen, but every green circle here marks a globular cluster in Centaurus A. So you can just see how they're distributed. Lots are around the core, which would make sense, and there are fewer further out. And all up, there's around, I think it was 1,108 globular clusters in this field of view, which is just astonishing, given that our Milky Way has 170 or thereabouts. And this is the same view, but just with the globulars. I'm not sure whether it's clear on the YouTube stream, but there are lots of little dots everywhere, and these are only the globular clusters. So no background galaxies or anything. This is sort of a clean image of the Centaurus A system. So Centaurus A itself with the dust lane, the jets, the shells, and all its globular clusters. And then no other background sources. So it's quite fascinating. You can find this image on my website in a high resolution version. It's probably easier to see there. But just a close up gives you an idea. So every point source here is an actual globular cluster in Centaurus A, and you can see it's completely full of them, which is just astonishing. All right, and then lastly, I just want to mention, once I had made all these different sort of editions of the image, I did want to combine with other wavelengths. So this has been done before, and I've been involved in a couple of collaborations with NASA around doing this. So comparing with the professional data from Centaur, the X-ray data, the UV from Galactic, Spitzer data, radio data, and you can create this sort of multi-wavelength view that shows everything that is going on in the galaxy, and it obviously does get very cluttered. I have tried to combine 6 different wavelengths of light into this image, plus the narrowband jet. So you can see the Chandra X-ray is the blue light in the middle there. That you can clearly see the jet beaming out, and it's sort of going in the direction of the inner filament there. There's some light from Galactic, the UV light. So you can see the blue stars at the edge of the dust band are very prominent there. It's very bright. Obviously, there's the whole optical layer, which is my own image. There's the Spitzer infrared image. So that's the red in here. It becomes difficult to see when they're all overlaid. But you got some more far infrared and sub-millimeter from Herschel. This is an older image, but it has a lot of structure further out. There's some big sort of cold hydrogen clouds that are further out. And then lastly, you got the radio lobes that are coming out, and you can see how they nicely overlay with the X-ray data. So yeah, this image is like a starless version of Centaurus A with all the different wavelengths that we have to date. So yeah, I've had great fun working on this project. It's taken 10 years or more, but obviously it's not been. I haven't been working on this every single day, but it's nice to sort of come back to this every now and then. And I'm sure that I'll probably find a new angle to this in the future. Take some more data. I'm already taking more data of the narrowband jet here, because I know that there must be more to see there. So I'm cracking away at that, and I will produce an updated version, I'm sure, at some point. So that's really it about Centaurus A. And if there are any questions, I'm more than happy to take them.
Oh yeah, well it's just amazing. So, and I think a lot of us are just sort of sitting here with our mouths open, looking at the image, because it's really one of the most impressive images in terms of detail that I can remember seeing. So we do have a few questions. Let's see, what probability cutoff did you use for determining if a source was a globular cluster or a quasar?
Oh yeah, that's a good question. I can't remember off the top of my head, and it's a little bit gut feel, right? Because that's how it's given in the Gaia data. It's not a binary yes or no. So you just gotta go with what you feel comfortable with. I think I set it to like 70-80% probability that it was a galaxy, and that was good enough for me. Something along those lines.
That makes sense. And then let's see. So we've got 3D space mapped on a two-dimensional surface, of course. So how to determine that there's strings of galaxies when they're in a 3-dimensional spatial frame of reference?
Yeah, so that's about the cosmic wave image. So obviously, I cannot prove that what we see in that image are sort of cosmic wave strings, but I can just see that it doesn't look like a random distribution. It looks very clumpy, and it looks like they flow along these strings, which is very similar to what the supercomputer simulations show. But yeah, I have no way of sort of examining every one of these 20,000 galaxies and finding out where they truly are in space.
Sure.
But yeah, I believe that it does show that kind of structure rather than a random distribution.
And
I've got a couple of questions myself, and Tarek had one a little while ago that we may have gotten lost while we were messing with the sound, because that's when you did a little bit of your biography. But are you doing all this as a hobby, as a study, is it related to your work at all, or what?
No, so this is not related to my work. So I work in IT, which sort of helps with the computer side of things. But other than that, yeah, no relation to my work. This is a hobby, and yeah, I'm able to take these very long images because these days I have this fully automated setup in the dome. Like if I had to carry my telescope and all my equipment and cameras and out every night and set it up and break it down again, there's no way that I could do this. So automation is a key to this. But yeah, it is just a hobby. It's just fun to do.
So how many nights a week you sit there and go, hey, go take these pictures for me tonight? How does that work?
Every single clear night, unless there's some reason that I can't. But every single clear night, I will just make sure that the telescope is working on something, right? So it just gathers data, and every morning after that, I can then download the data to my own computer, and then I just store it there until a rainy day when I feel ready to work on it. And I think that's the practical aspect of this hobby, that I can keep this running. It does not interfere with my family life or my work. It can just run overnight. It's fairly low maintenance, and then when I have the time, I can then combine it into actual images. So yeah, it's sort of I think once you have the setup, it's a low impact hobby that you can do when you have time.
Rolf, you can
go ahead
and
stop
quit
sharing your
sharing.
screen before we do the rest of the questions.
Okay.
You want me to
you
stop
can go ahead
sharing?
and stop sharing if you like.
Yeah.
Then while you're talking to us, you'll be just talking to us. Now, I had another question of my own, because you have a 683, a QSI 683. That's an APS-C size sensor, right? It's not a full frame sensor, right? Okay.
Yeah. It's what is it? It's the CAF 8300. So what's that?
Yeah.
It's like 3,200 by 2,500 or something pixels.
Yeah, right.
It's not big by today's standards.
And what I found, have you been using it for all those pictures you showed us? That was off the 683?
Yes, except that the webcam image I showed on that slide that showed the sort of progression from very early days. I had a webcam image on there, but yeah, everything else is with that sensor.
Okay. I just got to ask, how did you have spider veins in there, right? And you get a little rotation with spider veins, they don't match up anymore. How did you manage to be so perfect for like the last decade and a half of your life, having all that stuff lined up just perfectly?
Yeah, no, that's a good question. So I mean, it obviously only impacts the cross-shaped spikes on the stars. So yeah, I simply had to choose sort of what's my best star spikes in my data, and then just go with that. But yeah, the stars were not my focus in this either, right? I do have a version with stars, but that was not the main focus. So I went with that, and I have to say I use actually guitar strings to hold my secondary mirror. So each vein has 2 strings, and keeping them aligned all the time is just not happening. It's impossible. So my spikes will vary a little bit and be a little bit fat from time to time. So I tend to, when I make star spikes, I tend to sort of choose what's a good stack of just the spikes, and then I do have to sort of hand tweak them or clean them up a little bit to make them look nice. But yeah, otherwise it looks a little bit silly sometimes. But it depends on what I'm imaging. It depends on the angle of the telescope or how well collimated it happens to be. So yeah, you just gotta choose. But yeah, in this project, the stars were not the main focus. So
Right. Well, no, I mean, we only saw the stars in the first part.
Yeah.
But then you went to starless in a lot of them. But
yeah.
those stars looked like they had spikes, like they should have.
Yes,
So
yes. Yeah. So I can just, I mean, with that much data, I was able to choose the best spikes and stack them up, and then tweak them a little bit to make them sharp and nice. Yeah.
Okay. Thanks. And I do think we got all the questions out of there, out of chat.
So.
I think we did too. I had a question though. I was curious about the narrowband contribution of that image. Certainly, it appears that the bulk of the imaging time is broadband, but clearly you've got some HA and O3 as well. How much of each of those do you think is in there?
There's 126 hours of narrowband all up, and I think it's like 70 something hours of hydrogen alpha, and the rest is oxygen.
And you're going back for more, huh?
I've gone back for more. I'm working on it right now. Yeah.
Well, that O3 contribution is really interesting, and because certainly, you at least what I've seen, that this particular object, it tends to be a broadband image, or you'll see the HA added in, but the O3 is a nice detail as well. So
yeah. There's not much O3 to see, but I think if you get a really deep one, there might be more, as I've sort of been able to reveal in the hydrogen alpha already. So yeah, more is always better.
We'll have to get you back on to talk about the Cosmic Web project as well, if you want.
Yeah. That's a nice one. The video is quite interesting, so I recommend people have a look at the video there.
I got the link for that one posted as well in the chat, so people can.
All right. Yeah, and I can email you those links as well if you want me to.
Yeah, we'll put those in the episode description as well once we're finished here. But and that was a really neat insight. I not heard anybody talk about that before, but it makes perfect sense, because there certainly have been a number of times where I'm sure we've all just sort of looked at the stars, and they seem like they kind of line up, and sometimes in little patterns, lines here and there, and I was just figuring, well, it's just random, but maybe not so much.
Yeah. No, the galaxies are not random at large scale, at least. Yeah,
sure.
So yeah.
All right. Well, this has been great, and we got a lot of comments. Folks really enjoyed the presentation, so we really appreciate you coming on here, Rolf. This was really enjoyable.
Yeah.
So
thanks so much for having me.
Please hang out after we end the live stream. Forgot to mention this earlier. If you would like to chit chat.
Yes, thanks. And thanks everyone, and you too, Rolf, for sticking with us, bearing with us through the audio hiccups at the beginning. So I'm glad we got all that squared away so everybody could enjoy the content. And with that, we will see you all next week. So good night, everyone.
Good night.
Have a good night.
Thanks, guys.
Good night.